I must confess that after the last session this morning, which was What is a City, I thought that to really throw away this talk really and just talk more about what is a city, because there were some very fascinating things. And in fact, we've done quite a bit of work recently on thinking about what happens as cities get bigger. And the emerging wisdom in Britain is that we really only have one city, it's London. And there's been so many flows going out of London, back to London, basically for the last 2,000 years, basically, etc., that it's pretty hard to distinguish one from another. Anyway, that's something that maybe we'll revisit. What I'm going to talk about is networks, and in particular, of course, it introduces the idea that networks are also part of cities, etc. And one of the striking things this morning is we didn't say very much about flow systems and networks, so I'm going to try and redress the balance. So quickly, I'm just going to make the point that networks and flows are the glue that keep the city together to some extent, but of course there are so many different types of networks now that there is quite a big theoretical dilemma about how we make sense of all of these. So I'll say a little bit about that and show you some pictures of networks, and then say a little bit about big data. And then really there are two examples I want to look at. One is really scaling networks to systems of cities. And this is the notion that the bigness in terms of data really comes from thinking about networks. Clearly, obviously, the bigger the network, we're talking about an n-squared phenomenon here. So basically, the bigger the network, then the bigger the data set. I'm going to really look at two examples. One is scaling networks to systems of cities. I'll show you a little bit of work we're doing. And this, to some extent, will be a sample of these slides. There's probably far too many for the 20 minutes. So the first will be scaling up networks to, in fact, the entire country, to Britain. And at the same time, to introduce this notion that big data is not just about the domain data that pertain to these particular models and ideas we're talking about. It also pertains to the actual use. When we run the model I'll talk about in real time from the web, which indeed you can do, then every time it's run, the different user will be generating data. So the data can multiply quite dramatically simply by using the system that we've devised. To some extent, big data is really all about that. I mean, the power of Google, etc., really is the notion that there are not only kind of searching basically millions and billions of records, etc., but also generating their own data. And my second example will be at a really very different context, is to look at real-time streaming of data. This, if you like, is the high-frequency city compared to the first example, which is the low-frequency city. And I'll show you a little bit of work we're doing with our Oyster Card data set. That's a very big data set. That's 1 billion records for 3 months' worth of data, tap in, tap out in central London, in London, I should say. And in that context, we're really learning about mobility. So the kind of general title of this entire 3 talks really is Big Data and Planning Support Systems, etc. So to some extent, my examples really pertain to planning support and indeed big data. Okay, so let's actually begin by thinking about networks and flows. The origins of the city as a network go back a long way, certainly to Leonardo, who talked about rivers and nervous systems and things like that. And if Leonardo talked about it, probably the Greeks did. So here's a couple of pictures of early versions of networks. They're very interesting. The one on the bottom left is a network of flows in 1837 in the Pale of Dublin, basically. Dublin in those days was, of course, controlled from London, basically. It's part of Britain in that context. And this was a measurement of flows in 1837. Haas was a captain in the British Army, basically. And you have to ask the question, what was the British Army doing in Ireland in 1837? Actually measuring flows. And these flows would be horses and carts, pedestrians, etc., carriages, and so on. And of course, if you think about the wider context, what they were actually doing is, well, let's go back just to go across the water in Liverpool, Manchester in 1829 was the first passenger railway. So they were trying to figure out whether it would be worth actually building a railway in Ireland. It was the beginning of the railway age, in a sense. And in a sense, that kind of flow map is really writ large in everything that has gone on ever since. On the right-hand side, we've got Ravenstein's flow map, 1888. It's a kind of vector field. It relates to Luke's thing this morning in terms of the vector field. This was Ravenstein kind of I guess he didn't use the machinery of calculating vector fields in this context, but he gave the predominant flow from these Irish counties. In fact, the whole thing is from Britain. And in fact, he used a gravitational model in that sense now. Okay, so here are some flow patterns for cities, etc. Another map, top left, which is 1729, flows of the turnpike roads around London, and then Unwin's map of in 1902, the middle top, which is flows into London, and then something we did in terms of retailing. That's the top right is the retailing map. And then there's the Oyster Card map that I'll show you a little bit later on of flows, basically, which is an animation, effectively. I haven't got time to show the animation, but it goes on a second-by-second or minute-by-minute basis for a synthetic week of flows. And then there's a map from Alistair Ray showing concentration of municipalities in and around London in terms of journey to work. So that's quite recent in this sense. Okay, some more flow maps here. Here's Paris, basically Minard's map in 1850s. And then, in fact, Benton Mackay had to show something in terms of Boston. This is from his book, The New Explorations in the 1920s, basically showing inflows and outflows. And his thesis was that to look at flows, you have to really look at the wider region. And he was a professor of forestry here at Harvard and was really looking at the water catchment, etc., the catchment area, etc. And then on the bottom, more flow maps that are giving you some sense of networks, etc. The one in the middle is one of the Palm Islands in Dubai. And you can sort of see how flows penetrate into this hostile media. They're building these islands basically in the interstices between the leaves, basically. You've got the places where they park their boats, and then on the leaves themselves or the branches, you've got the high-value houses, etc. And then, of course, all of this sort of stuff relates to ways of thinking about these morphologies, fractals, etc. Okay, so linking networks. There are lots of these sorts of networks appearing, and I'll show you a few more in terms of social media in a moment. But one of the kind of key things here is that we don't really have a good theory for knowing how networks and markets determine activities and locations and change in cities. That, in other words, networks are really central to how energy and information get distributed in cities, but we don't have good theory in any sense, both about the networks themselves and the flows. Network science, which has developed over the last 10 or 15 years, tells us a little bit about the statistical properties of networks, but it doesn't really relate very much to flows. What flow theory we have is spatial interaction, gravitation, inter-industry relations, things of that sort. And again, these things are not joined. Add all of the social media networks together, the social networks and so on, and then this is the nature of the problem. It's almost what Doreen Massey in her book on space has called thrown togetherness, basically. That in other words, the theories we have about cities are lots and lots of different ideas, this great kaleidoscope of ideas where things are actually thrown together, really, in some senses. And that's the nature of the problem. And it may be a problem that is endemic to our field, etc. These are the kind of big questions, I think, that we need to think in that context. So lots of new data, etc. Here's some Facebook friendship links taken from the web. And then we have the nightlights photo. It's a good one of Tokyo, basically. That's energy, essentially. And then Flickr locations, London, and tweet locations. This is taken from Eric Fisher's work. And then tweets across Europe. I like this bottom right example because if you think about Brexit, does that mean that all this is going to end, basically? The flow looks as though it's flowing out of Europe into Britain, basically. Of course, we're really only talking here about tourists, basically, sort of tweeting predominantly, which is probably the case in this particular data. Okay, and lots of things with respect to methods for dealing with networks and flows. There's a lot of work going on scaling, for example. I know Art Gettis is going to talk about Zipf's law later on this afternoon, so he'll talk about scaling, but there are lots of ideas about scaling in networks, Laszlo Barabasi's work, etc., and Duncan Watts and people like that have talked about small world problems as examples of scaling, etc., power laws and so on. And there's lots of geometrical methods that really look at self-similarity, such as fractals. Myself and Paul Paul Longley, basically, about 25 years ago, wrote a book called Fractal Cities, which was really all about these kinds of morphologies and how one could make sense of them statistically and also visually in that sense. Okay, so that's the background generally. An interlude about big data. As soon as we start talking about networks in that sense, then we're really talking about potentially big problems in this context. Now, the PDF here is slightly, or the slide is slightly wrong. Basically, let me tell you a little bit about an example. I can't go into it in detail, but it's so fascinating that it's well worth making. Back in the 1950s, there was a computer installation which had been developed for what was called the Lions Tea Company. Back in the 1950s, when I was a little boy, the McDonald's of its age, the fast food of its age, was the tea company, the Lions Tea Company. There were Lions Tea House everywhere. They had a massive supply chain problem, and they'd picked up a bunch of guys who'd worked at Bletchley with Turing during the war, and they put together one of the state-of-the-art computer systems to deal with their supply chains. Now, this computer system that they had was underutilized. They switched it on in the morning, basically, and they had spur cycles, and so they decided to rent it out. This was around about 1955, and British Railways in those days wanted to compute the rates for shipping freight between their key stations. Now, this is where, and the number of stations was 5,500. It's not 1,500. I had to look at it again before I actually after I'd done the PDF. It's 5,500 stations. The problem is the order of n squared, and then the matrix was quite large. It's 500 by 500, 5,500 by 5,500, which is about 30 million cells. So this was the nature of the problem. Now, they had a computer to do this that had 2K of RAM, not 5K, 2K of RAM, and it had mercury delay tubes to actually store the data, basically. They had punch cards, they had paper tape, and so on. And how the hell did they do it? Well, I don't have time to tell you how they actually solved this problem for British Rail, but if you go to this YouTube video and watch John Graham Cumming, who is a cloud computing guy, works for Cloudflare, he has a great story about the great railway caper, big data in 1955. This really was big data. And one of the fascinating things about this story is that on the way to solving this problem, they divided Scotland off from England and Wales because there are only two rail lines going up Scotland, west and east coast. So they solved the problem and partitioned it. They actually invented an algorithm which is called Dijkstra's algorithm. They invented it in 1955, but of course Dijkstra did not publish his famous shortest route algorithm till 1959, basically. And when John Graham Cumming went back to talk to the guys who were still alive, basically, 10 years ago when he gave this talk, they'd never heard of Dijkstra. They were computer scientists, but they never heard of Dijkstra. They went off to work for BT and all this kind of thing, and the BBC and so on. And in that context, his point really is that big data not only forces ideas about how to handle the big data, it also forces the development of algorithms to deal with it in this particular context. So it's a particularly good example in this context. Now, I've always dealt with biggish data, and of course we're making the point here that big data is relative to the computers you have. So in my book back in 76 on urban modeling, you can see these flow diagrams here, and the bottom line basically is Greater London divided into its 33 constituent municipalities, and basically showing you that in this context it's difficult to visualize the pattern even in something that's only 33 by 33 1089 matrices in this particular context. Scale it up to anything realistic, and this is basically what you get. We divide London into its wards, which is 633, and then you just get a great mess in a sense. So one of the great challenges is to make sense, and this is really a visual demonstration, but to make sense of what all this means in terms of these flows. A lot of the visualization techniques that have been invented in the last 10 or 15 years really don't cope with this size problem at all. There's a classic example of showing the flows between London boroughs, basically where they're arranged around the edge of the circle in the top left. and these U-shaped things are the flows from the borough to itself, which is normally greater than between boroughs in this context. So you can see the nature of the problem. And of course, many of our statistics break down, even with this data here, where we're talking about 400,000 cells potentially. In terms of looking at the distribution of data, it doesn't really conform in any sense to what we read in the statistics book. Mainly our statistics really relates to the 1920s, to genetics and Fisher and Pearson and all these sort of people, and the scatter diagrams are 100 or 1,000 points even. But when you're at 400,000, or when you're at 400 million, basically, then things really do begin to break down. So the challenges of big data are not just to storing it and manipulating it, it's also to actually dealing with the right kind of statistics, the right kind of pattern analysis to make sense of it. Okay, now my first example, how am I doing for time, Chairman? 10 minutes? Okay, very good. Okay, my first example is scaling these networks to systems of cities. The problem we've wanted to look at in our group basically was how we take our land use transportation models, of which these flow data is really basic, and scale them up to something bigger than cities. Most of these models, in fact almost exclusively, have been employed for cities. And of course, as computers have got bigger and faster and so on, then the problems have got greater, the level of resolution has got finer and so on in that context. And we thought we would have a go at scaling them up to Great Britain, basically. That's the British island, basically. We not worrying too much about Ireland itself or Northern Ireland in this context, but to begin with. Now, of course, we've only done this really for England and Wales. You often see maps of England, Wales and Scotland where you've just got England and Wales, or even just England basically, so it looks a little bit odd. The reason why we've not included it for Scotland as yet is because Scotland have a different regime when it comes to the census. They have their own Registrar General. Their census is pretty integrated with the England and Wales census, but at this point when we started the project about 2 or 3 years ago, then Scotland had not released the journey to work data, which is pretty central to the whole thing for there. So we fully intend to add to it. Now the second example I'll talk about is much more fine scale, but let me first of all deal with the first example. We've divided England and Wales into what are called middle area super output areas, which is roughly the equivalent of wards, about an average of 7,000 persons. So we're building a land use transportation model for 7201 squared, which is about 52 million cells in the matrix. That's a pretty big matrix, even by current standards, at least if you're wanting to get immediate computation, immediate results, etc. In that context. And we have several of these things. So in other words, 52 million points, basically, or 52 million cells, essentially. In that sense, it's a sparse matrix, but we can't really take much availability of that. It's not easy to partition it in some way and deal with it in bits in that sense, so we deal with the whole lot. And we're very interested in the fact that we need to deal with the whole matrix because in terms of making forecasts for the future, some of these potential links which might have very few flows or zero flows will have flows in the future in that sense. So that's the problem scaled up, basically. That's what we're actually grappling with. And here's a picture of the zones themselves. This is the middle layer super output areas for England and Wales, and you can see they are finer in the urban areas, so that's a good map really almost of urban development in Britain in this context. We could go lower, we could go to the lower level super output areas or the output areas themselves, which have got 181,000. That would be 181,000 squared, which would be a massive matrix in some sense, many orders bigger than the amount of flows themselves in this context. So that's another kind of issue. Okay, now the whole thing in terms of this problem is to put the thing onto the web, because the reason for doing it is we want local authority planners, and this is where the planning support system things come in, to actually log onto the model and use it to test scenarios. If we want to put a new rail link in, or a new road, or if we want to put a new population or new employment, we want the planners to be in a position, the policy analysts to be in a position where they can do it on the fly. And we want them to be able to do it everywhere in the UK, basically. So if you're in Cleveland, or if you're in Carlisle, or if you're in Cardiff or somewhere, and you're interested in looking at the impact of new employment or new roads, etc., new transport links, then we want them to do it, and we want the data to be, we want the models to be run in real time, basically. So this is our quant model. If you log on to that link, then you'll see a rudimentary, you can do it on your phone, basically, if you want to, but I wouldn't advise you to, because you'd soon find it was a bit slow. It's quite fast in the hotel room this morning. I was quite surprised. I mean, everywhere I go, I test it and see how fast the link is, basically. It was quite fast. It's quite amazing. So I can't do it now, but basically, there's lots of things in the model. We use these vector fields, as Luke talked about this morning, basically, to summarize. We don't have these flow diagrams everywhere. We have vector fields, and you can see the vector field for England and Wales. This is from the journey to work, and then the one zoomed in. So the arrow actually shows you the predominant orientation of the flow. Think of all the flows from one of those arrows, one of those points, all the way around. You take the average of that and you take the average orientation to actually get the vector, basically. So it's a way of summarizing a big matrix in terms of these flows. That's typical of the interface. You zoom in, the map is served in that sense. Those are the green belts, that's accessibility. And to show you what we do in this context and what this is all about is that we're actually testing big infrastructure projects in the UK at the moment. Our biggest infrastructure project that's about to be finished is called Crossrail. It runs from Reading to in the west to Abbey Wood with a spur down to Heathrow. It's been 30 years in the making. It's the equivalent here in Boston of your Big Dig. And it's suffered all the same problems as the Big Dig. It's taken forever to do. It'll come on stream, and there'll be one train every minute, something. And the underground section is the red section in central London. It means that if you get into Heathrow and you want to go to, got to be careful here, if you want to go to Liverpool Street, you'll be able to get there in one go, basically. I nearly said King's Cross there, but I don't think that. I think you've got to change one stop to get to King's Cross. But nevertheless, it's going to improve things quite dramatically. We're looking at lots of other things in Britain. We're looking at East-West Rail. That's the proposal to link Oxford and Cambridge across the top, to put back the railway line that Beeching closed in the 1960s, because that's where all the high-tech stuff is going, across to Milton Keynes. And so East-West Rail in this context. We're looking at HS2, which is the new proposal from London to Birmingham, Manchester, and on to, to Liverpool and to West Yorkshire, and ultimately to Newcastle, we think, and Humberside. We're looking at lots of local railway lines in that context, and we can do this more or less on the fly. One of the interesting things about scaling up is that this is the number of improved journeys with Crossrail. And if you look at the little inset map of the UK, very large numbers of places would benefit by Crossrail. If you are coming from Berwick-on-Tweed on the Scottish border down to Brighton, you may never use Crossrail because you would cross over London and never use that line. So there would really be no improvement for that journey. But there are many, many journeys you would make where there would be improvements, as you can see in terms of this context. And we've looked at population change, and as the model basically works on three modes, road, rail, and road, rail, and bus, basically, then this is showing you the switch in population by putting this line in across London. Okay, right, my second example. Very quickly then, 2 or 3 minutes just on the fine scale example, a complete switch in terms of example. This is our Oyster Card system, which is the tap in, tap out. It's the RFID card. You can pay. You can use your Apple phone. You can pay it with Apple. You can use a credit card, etc. It's quite flexible, the system. Now we've got a big database from Transport for London of almost 1 billion records over the summer of 2012, where we have 991 million Oyster Card taps over this particular 3-month period. The reason why we've got this data is because the Olympic Games happened in the middle of summer of 2012, and they wanted to look at the Transport for London wanted to look at the gridlock, which was anticipated but never actually occurred. So they needed an analysis of it. The data is very good data. It tells you everything about where a person taps in and taps out, highly anonymized, completely anonymized, etc. But the quality of the data is problematic. There's a lot of missing data. A number of people have freedom cards. If you're over 60, and it's no I'm sure you can work out that I'm over 60. You get a freedom card, so it means you don't have to pay. It's like a bus pass in that sense. And also people who have season tickets are able to get on. So if the barriers are up, you don't get fined. If the barriers are up and you're just a regular user and you actually don't tap in, when you get to the other end and tap out, then you would get charged the maximum fare. So that's the incentive to actually tap in and tap out. But in the data that the guys gave me, a big data set, they managed to get it down to the point where they could put it into an Excel spreadsheet for me, because I'm not an SQL user or anything like this. So, basically, in the day I looked at, November, it was a different data set, 2010, then 6.2 million people tapped in and 5.4 million people tapped out. And the tube closes for 2 hours. So where were these 0.8 million people? Were they on a siding somewhere, parked away? No. The barriers were open in that sense. Okay, lots of things. Now, this is typically Central Rail, a rail in central London. It's the tube map's in the middle of that, basically. So the Oyster Card works on all of that. Also works on all the buses as well, and some national rail in that sense. Here are some pictures of the flows. I can't show you the flow maps basically, but these assignment maps, you can just about make them out, I think, showing different times of the day. So we have an animation of this, and one of the fascinating things about the data, the big data, is that every segment on every day is different from one another. There is a routineness to the cycles, etc. You can see the morning and evening peaks. These are the tube stations, morning and evening peaks. So there's a routineness of that sort, but every link is slightly different, and that's due to the fact that if I go to the same place every day and I tap in at 9 o'clock, if I tap in at 9:01, the data is recorded differently. So there's an issue about aggregation in terms of looking for the pattern in that sense. We've done quite a bit of stuff on looking at this. There's some data, some stuff we did with Mark Bartholomew in Paris on the data back in 2011. There's a paper in PLOS ONE. And these are very interesting because for each tube station, we get these profiles. Now, I always say to the audience, these are different tube stations around London. The top right is the most interesting. I always say, where is that? And the answer, of course, is that's the Arsenal. That's Highbury. That's where the Emirates Stadium is. And those big peaks are the two Saturday games. This is a synthetic data set over a month. The two Saturday games and the evening game on a Wednesday or Thursday, whenever it is, the slight colour coding. So, in other words, you're getting a kind of a profile from this data. Now, that's not new. It's just that we're able to get it now. We've always known this sort of stuff. It's not surprising. But in some senses, it's actually profiling things. And we've had a postdoc CASA who is now a lecturer at King's, and she did a PhD in Singapore at the Future Cities Lab with ETH and the Zurich people, and she looked at Singapore. So we've actually compared London, Singapore, and Beijing. She worked for a couple of years before she went to King's, basically, in our group. And we've looked at Beijing and we've looked at Singapore, and we're looking at variability. So there's a lot of detailed stuff we can actually do here. We're interested in disruption. Kingsley's pushing me here to finish. Well, a couple of minutes. We're looking at disruption, etc. There's lots of things we can look at. Here, for example, is a case where the Circle and District line was down between Aldgate East and the Edgware Road. That was down for 4 hours in the summer of 2012. That line being down for 4 hours is no mean problem. It's a massive problem. People were delayed, and what we can do from the data is you can figure out where they go. We can even figure out if they get onto a bus, basically, but we can't figure out where they get off the bus, because in London you can only tap on. Because of the driver, you won't tap off. Okay, so we've done lots of stuff on this, and we've also looked at train times and so on, and delays, etc. So what can we learn from all this, just to finish off? We've got issues about confidentiality and data quality, etc. We've got issues about how you can interpret from this data what's going on, add value to it in terms of land use. Chen did a paper in IJGIS on how you can take the Singapore data and figure out land uses from it by merging a couple of different data sets. related to transport, etc. We've written a bunch of papers on it, and those are they. And let me thank people in my group who've been responsible for much of this. I'm really just the messenger. These guys do the work. Thank you.